All right, hello everyone. Welcome to another one of Mr. Martin's math videos. This is a video for British Columbia Pre-Calculus 12, Chapter 7, Section 1, looking at the characteristics of exponent functions. So we're starting a new type of function here that we're learning called the exponential function. All right, so today you're going to be introduced to another class of equations, exponential equations. These guys are most popular when studying population growth, concentration levels of a solute in a solvent, like drugs in the bloodstream or contamination in a lake river, RRSPs, radioactive decay and isotope. And next chapter we'll be studying the evil twin of exponential functions, logarithms. So good times ahead. Here as well, it's worth noting that during this COVID-19 pandemic, a lot of the graphs that you've been seeing definitely have that exponential quality as well. So we'll talk about that as we go through these notes. Some of these characteristics and some of the values that you may have heard in the news, like the R naught value, those kinds of things, are ways that these health professionals are able to make the predictions of, caseloads and death rates and those types of things. And so definitely very relevant to what we're learning about right now. Let's get started here. So what do you do with this stuff when you leave school and become an adult? Well, one of my favorite equations in this, kind of exponential equations is the one that allows you to calculate the value of an investment. This one right here, really valuable equation here that we looked at a little bit in grade 10 and has served me, well when I look at investment opportunities for myself and moving forward into the future. So one of the most important investments everybody should be putting some money into your RRSPs. Okay, Canada has TFSAs and RRSPs. They both have their pros and cons. We talked about these accounts a little bit in grade 10. But both are, it's good to fill up both of them. You want to fill up your tax efficient accounts as much as possible when it comes to finances. If you're watching this in the States, the RRSP and TFSA are kind of the parallel to your 401k or a Roth IRA would be probably the best two comparisons to those accounts respectively. This is a special type of saving account that grows your money to a substantial value over a long period of time. To demonstrate the power of these types of savings accounts, imagine the following situation. Bill is 18 years old and has a part-time job at McDonald's. Okay, great job. I worked there when I was in high school, loved it. He wants to open up an RSP and start saving towards his retirement. Imagine that Bill can earn an average of 8% on his investments, which is, within striking distance. If you're investing into some, index fund, maybe factor-weighted index funds, each year, how much does Bill need to save each month in order to retire a millionaire? So this is an equation that we looked at, actually, I think in grade 10. I don't know if you guys remember what the amount was as an 18-year-old starting to invest and trying to become a millionaire by the time he retires at 65, assuming that's the retirement age. If you remember, we won't go through the numbers, but the number that we had calculated back then, Bill needs to save about $161 per month, starting at the age of 18 without missing a payment or a savings kind of contribution, and then by the time he is 65 years old, he'll have $1 million in that account. Okay, which is pretty amazing how compound interest and exponential growth can work, right? Because that's a small amount, $161. If you're currently working at McDonald's, which I know some of you guys are, who are listening to this, or working at any other job, you're making $161 a month or more, right? If you're working at a grocery store, or even if you average out the money you make at summer camp or during day camps in the summertime, you can find this kind of money to start investing in now. And you have access to these RSPs and TFSA accounts right now as 18-year-olds, those of you guys who are 18. And so, no time like the present to get started and working. The earlier you start, the lower this number is in terms of how much you need to save to, end up with $1 million in retirement, if that's your goal. Obviously, if your goal is higher than that, you need to save more. But however, if you just wait till you're 30 instead of starting at 18, this number is going to be significantly, and it's not going to be like double. It's going to be like adding a zero to the end per month. So you're giving $1,600 per month instead of $160 per month for life, based on when you start investing. So really worth starting as soon as you can. Talk to me about it if you want to know more. And so here, if you want to, another kind of fun video on the power of exponential functions, look at how paper folding can get you to the moon, okay? But how do you know when you're dealing with an exponential function? Well, exponential behavior occurs when the function has a variable in the exponent, okay? So for example, kind of a basic exponential function we're going to be looking at in this chapter is going to be something like this: y is equal to c to the x. Okay, so here the variable is the exponent, or in the exponent position, all right, where x is our variable, okay, and c, and this is where a lot of students get confused because they take the c value as the variable, where the c value is not a variable in this situation. The c value is just a constant for the curve, okay? Of course, if you change your c variable, that's going to change your curve, but then you change the exponent, that's going to change the curve even more, right? So, all right. People, when they talk about COVID-19, they talk about that R0 value, which just means how many people are you transferring the disease to per individual. So initially at the beginning of the pandemic, they were saying that one individual would pass the COVID-19 virus to 2 people, right? And so then you have that C value would be 2, right? And so you had these exponential curves, and the time value variable would be like how many days have passed at that constant. And you'd have these equations, like this, where the number of cases were just going higher and higher and higher. But social distancing, what we've been doing with social distancing is, instead of having a y is equal to the y is equal to 2 to the x, where x is the number of days, let's say, that passes, what we're doing with social distancing is we're trying to reduce that constant value, okay? We'll call that R0 value. So if you can get that to like something under 1, and we're going to talk about that a little bit later in the notes. So for example, 0.8, okay, you're going to see that when you have an exponential function of something less than 1, then your curve is no longer increasing, okay? If you compare these two equations here, and if we just plug these in quickly just to apply this to our current situation, 2 to the power of x and 0.8 to the power of x, okay, and I'm going to graph both of these. Okay, I want you to notice the green line is what we were dealing with at the beginning of this pandemic, where we had that R0 value of 2 or 2.1 even at some point, 2.4 in some places. Really crazy. And so day by day, the number of cases just skyrocketed, right? In the United States, places like Italy, we're seeing this still happen in Russia and India and Mexico and Brazil at the recording of this video. But as the world is seeking to social distance, plus the quarantine measures that have been put in place, okay, what that does is, once we get an R0 value, so every individual is not giving it to 2 people, they're giving it to less than 1 person. Every individual gives it to less people. What we end up getting is a decreasing curve, where the numbers of cases are going to come way down, right? And that's going to allow us to flatten the curve and even reduce the curve, so that our medical, systems in our countries. Here in Canada, we have a pretty darn good one. But it still can get overrun if we're not careful. And so if we can get that R not value down to less than 1, then the number of cases are actually going to drop. And we've seen this already in British Columbia. BC's done a great job. That Dr. I forget her name, but she's done a great job here in British Columbia. And other countries have, been able to do this as well, reduce their rates quite significantly. So that's what, social distancing is all about, right? It's to change that constant value in an exponential curve so that instead of getting exponential growth, like the green line, right, we're getting kind of exponential reduction, like the yellow line, okay? So that's the math behind that. All right, so let's take a look at some of these examples here. So studying the shape and behavior of exponential functions. So linear graphs are straight, quadratics are parabolic, radical functions are like half parabola that got beat up and left for dead. Trig functions are like waves in the ocean, and exponentials are like really, really, really scary roller coasters. Okay, so let's take a look at what one of these might actually look like. And so what I'm going to do is I'm actually just going to create a table. So in grade 9, we learn how to draw a graph from an equation, and the step that we do is that we make a table, right, with x and y, and we just start plugging in values, right? So 0, 1, 2, 3, let's say. So if I plug in 0 in the place of x in this equation, I'm going to get a y that's equal to 1. If I put a 1 in the x, I get 4. If I put 2, I get 16. If I get 3, I put 64. Okay, so you saw that grew really quick. Okay, and if I put a 4 in here, you'd have an even larger number, which would be, what would that be? 240, 256, I think. 4 to the 4. Yeah, that's right. Okay, so all right, so let's plug that in now. So at 0, I have 1, so that's my first point there. At 1, I have 4. At 2, I have 16. And at 3, I'm off the charts. Okay. Now, also, if I were to go negative in the negative direction, okay, if I have 4 to the negative 1, okay. Clear 4 to the negative 1, not to the minus 1. I get a quarter. Okay, so if I can find a quarter, it's like this. And if I put 4 to the negative, 5, I never get into the negative numbers, but my numbers get smaller and smaller and smaller. And so my line approaches the x-axis, but it never crosses the x-axis. Okay? And then once it's in the positives, it's out of here. Okay, so that's what we can kind of expect from our exponential graphs. Okay, so let's look at some of these characteristics here. Domain and range. What's my domain? Well, x can be anything, right? X can be anything. Okay, but what can y be? Well, here I saw that there's a limit to y can be, right? What exponent can you put on a number to make it negative? The answer is there is no exponent you can put on a number to make it a negative. There just isn't. There isn't even an exponent that you put on a number to make it equal to 0, right? If you make an exponent if you have a number to the exponent of 0, it doesn't give you 0, it gives you 1, right? And so here for our range, here y is greater than 0. Okay, it can approach 0, but it will never reach 0. Okay, but it's a solid line, so we're still dealing with all real numbers here. So that's my domain and range, and that's going to be a pretty common domain and range for all rational functions. All right, x and y intercept. Okay, well, x-intercept, we just said that there is no x-intercept, right? It's not going to cross the x-axis. There is no x-intercept. What about the y-intercept? Well, the y-intercept in this situation is 0 and 1, right? And that's going to be the y-intercept for most of our equations, because no matter what the constant you choose, let's say I pick 445 exponent 0, it's going to be 1, okay? It doesn't matter the number. If you put it to the exponent of 0, it's going to give you 1. So that's going to be a very common, unless the graph has been transformed, unless your exponential function has been transformed, you're going to get a y-intercept of at 0 and 1. Okay. Is this function increasing or decreasing? Okay, well, it's pretty clear in this one that this is an increasing graph. We saw in the example for COVID-19 a decreasing graph. We'll see another one in the future here in a second. But yeah, this is an increasing. And you just read that left to right. Okay, you read your graph left to right. Is it increasing or decreasing? And then the equation of the horizontal asymptote is y is equal to 0. Okay, the horizontal asymptote is that line that the line for our exponential function approaches but never crosses. And in this case, it's the x-axis, right? And the equation for the x-axis is y is equal to 0. Awesome. All right, let's look at some examples here. Actually, see if we can determine our equation now, work backwards from the graph to an equation. Okay, and we're going to take that Math 9 approach. We're going to go from the graph to a table and then to the equation. So here, I want you guys to try this out on your own. Pause the video, do this one, and then do this one. Okay, try to determine the equation from the graph provided. All right, go ahead. All right, hopefully that went well for you. Let's take a look at this together. So I'm going to take from the graph, I'm going to make a table. I have x is equal to 0, 1, and 2 on my graph, so I'm going to plug those in. When x is equal to 0, y is equal to 1, not surprising, okay? When x is equal to 1, y is equal to 5, and this is an important one, right? And then this is just a confirmation one. This is an important one because when you're dealing with y is equal to c to the x and you're trying to figure out what c is, okay? C is going to be what y is equal to when x is equal to 1, right? Any number to the exponent of 1 is just that number. It's like multiplying the number by 1, right? It's just the number. If I say 5 to the 1, that's equal to 5. If I say 12 to the 1, that's equal to 12, right? And so this is like by far the most telling value there for sure. Okay, when you're dealing, if you have a positive x exponent, okay, when you're dealing with an equation, that's a good hint there. So this would be our equation, right? Y is equal to 5x. That one's pretty straightforward. All right, and it works, right? Because if you take now that 5 and make an exponent of 2, I get 25. So, it confirms. So y is equal to 5x. All right, let's do our second one. Here, I have this equation. Now I have, I'm going to start with my table again. Here I got some different values. I have -2, -1, and 0. Okay, so at -2 I have 16. At -1 I have 4. And at 0 I have 1. Okay, well that's not surprising again. Okay, so now I gotta think about, okay, what kind of C value gives me a decreasing line? Okay, would it be a negative? Having a negative C value is a little bit weird. I just want to show you guys what that kind of looks like here. If I said I had -2 to the x, right? To the x, right? And I tried to graph that, you're going to have a hard time graphing an equation like this because I don't know if you can see kind of the lines dancing up and down here because it's going to go back and forth so much. I don't know if I can even have it show up because it's going to be positive and then negative, then positive and negative, and so essentially your graph is going to go up, down, up, down. So it's not one that we don't have a C value that's negative in this chapter. Okay, we're going to keep our C values positive. All right, but that being the case, that doesn't mean our C values will always be whole numbers. They're not always going to be, integers. And so that's what you got to think about in this case here. So what situation what value of c, right? If you had this, so for example, what value, if the answer was 16, what would c, what would c be here if I had -2? To the -2 would give me 16, okay? One way to kind of help you with this is to think about, okay, well, let's think of the positive, okay? So if 16 to the c squared, in this situation, what would the c be, right? In this situation, it's obvious that, and I'll use a different variable just so we don't confuse. Let's use b. What would the b be? The b would be 4, okay? So if x was +2 and I got 16, the b would be 4. So in this situation, if c to the -2 is equal 16, okay, now we can remember what does the kind of a negative exponent do to a fraction, right? So if I had 1/4 to the -1, right, that would give me 4/1, right? That would actually flip my, because that's how you make an exponent positive, right? We talked about this in grade 10, I think, where this to the -1/4 to the -1, I would flip the 2, and that would give me 4 to the 1/1 to the 1, which would equal 4. Okay? So in this situation, and this would work as well, right? Because we have, that would give me this point here. So that actually is a good value for c. And this question would be 1/4. Okay, and you can test this as well, right? You can do 1 divided by 4 exponent to the -1, and I get 4, right? You can test that out. All right. So in this situation, we get an equation of y is equal to 1/4x would be my equation, okay? Because that would be a c value, would have to be a value between 0 and 1. First of all, because I have a decreasing graph like this, that means your c value is going to be between 0 and 1. It's going to be less than 1, okay? Just like that 0.8 R0 value we used as an example for the COVID-19 numbers. And then you can figure out what that fraction is based on some of the recognizable multiples that you have in your x to y kind of table that you came up with. Okay. So let's take a look at a couple of these, kind of flesh that out a little bit more. So types of exponential equations, we said that there was an increasing and decreasing equation. So an increasing exponential equation undergoes exponential growth, right? That's why we use increasing equation, hopefully an increasing equation when you're talking about financial investments, because you want growth, you don't want decay. The way some people invest, they're actually investing in decay, not growth. But you're aiming for growth, even in this time of decay with the stock market as it is. There's opportunity for growth. Okay. And does so when c in the function y is equal to cx is, in order to get an increasing exponential function or growth in your exponential function, c must be greater than 1. Okay, you just need to have c greater than 1. Okay, so if I were to apply this to kind of COVID-19 again, as long as that R0 value is greater than 1, as long as that R0 value is greater than 1, we're going to see numbers continue to climb in COVID-19, okay? That's why it's so important to reduce this number to less than 1, because once that number becomes less than 1, then those numbers, this becomes a decreasing exponential equation, not an increasing exponential equation, okay? And we experience a decay in the case numbers of COVID-19 instead of a growth of numbers in COVID-19. And does so when the function of y equals c to the x is between 0, let me write this clean, 0 less than c less than 1. Okay, we're not going to use negative c values. We talked about that already. but you get a C value that is between 0 and 1. Okay, and once you get that C value between 0 and 1, then you have a decreasing exponential decay. Okay, so let's model this kind of decay. Okay, one example of that we talked about with COVID-19. Another example of that is with radiometric dating. Okay, radioactive samples of radium has a half-life of 15 days. If you haven't studied half-life before, half-life is the amount of time for half of the substance in the, or half of the mass of the substance that you start with to decay to a different substance. So let's take a look here. So the mass of M in grams of radium-225 remains over time t in 15-day intervals can be modeled using the exponential growth shown. Okay, so in 15 days, if you had 100 grams of this radium-225 in 15 days, that's how much time it would take you to get to 50 grams. Okay, and another 15 days, how much grams would you have of radium-225? Not 0. You would have half of the previous, which would be 25 grams, and then half of the previous, which would be 12.5 grams, and so on and so forth. Okay, the amount that's being radioactively decayed is it follows this pattern, okay, which allows us to then predict how long it's been radioactively decaying for, which is why some of the numbers for geology and so on use this method for radiometric dating, not without controversy. Right, so it's multiply times 1/2, right, in 15 days times 1/2 in 15 days. So it's not 50 in the first 15 days and then the other 50, okay, which you might expect, but that's not the case. It's 50 in the first 15 days and then half of 50 in the next 15 days and half of 25 in the next 15 days and so on and so forth. Okay. All right. So what is the initial, according to this sample here, now I used 100 grams, but the graph says what is the initial amount of the sample that we start off with. So the graph says we start off with 1 gram. And what value does the mass of R225 remaining approach as time passes? And it goes from 1 gram and approaches 0 grams as time passes. Okay, well, the power of this dating method is because it's approaching 0, but we know that even a decreasing function will not reach 0, at least in theory. We can know that so these sequences, even though after 15 days most of the mass of this radium-225 is gone, this tail of the graph here can go on for a very long time to very small numbers. And so that allows us to make predictions for long periods of time. So what are the domain and range of this function? Okay, well, here we use a practical domain, so we have to start with x being greater than or equal to 0, right? You start on day 0, you don't start on day -3. And then, of course, it's any rational or any real number. And then for the range, y is greater than 0, and it is all real numbers as well. All right. Oh, wait, I did the y wrong. Okay, so y also has a maximum, right? Y has a maximum of 1. So let me put that on there. 0 is less than y, which is less than or equal to 1. Okay. Write the exponential decay model that relates to the mass of radium-225 remaining in time in 15-day intervals. And so here you'd have the mass remaining as a function of time. Okay, and your equation would be 1/2 because it's a half-life, so half of the mass. You're multiplying by 1/2 over and over again, x amount of times. Okay, but that only happens every 15 days. So if t is my exponent, t is equal to some multiple of 15. Okay. Or t is equal to a 15-day period. So if it's 30 days, then t would equal 2. Does that make sense? I don't know if I expressed that as clear as I could have here. So if it's 45 days have passed, then t is equal to 3, and so on and so forth. Okay. So now we want to estimate how many days will it take for the radium-225 sample to decay to 1/30th of its original mass. Okay, well, now I set up this equation. 1/30 is equal to 1/2 to the t. Here for now, I mean, obviously we're going to be dealing with logs just in a second, so we'll have an equation to go from exponential to logarithmic form, which will allow us to solve for these missing variables here. But for now, we can just use kind of the guess and check method here for this. And so, I can know in decimals that this is about 0.03 repeating. So what exponent of 1/2 would get me that? Okay, so if I to the 3, not quite, 1 divided by 2 to the 4. Okay, I'm getting there. 1 divided by 2 to the 5. Okay, I've passed it. Okay, but I'm close to that 5. So then you can imagine 1 divided by 2 exponent of 4.8. That's pretty close. 1 divided by 2 to the 4.9. That's pretty close too, and that's maybe as close as we can get here. So given the guess and check method, we'll use 4.9 half-lives. But t is a 15-day period, right? So you'd have to do 4.9 times 15 days per half-life. Okay, so it would be 4.9 times 15. So we're looking at about 73 to 74 days. Okay, so that's kind of how you'd approach a problem like that. Okay, eventually I'll be talking about how to go from logarithm exponential function to logarithmic function, and that allows you to then use your calculator to solve for that t value. But for now, guess and check will get you through most of the questions that you'll be facing. So your homework there at the bottom, 7.1, due next class on Wednesday. And if you have any questions, reach out to me either on Teams or on the channel. And hopefully this has been helpful for you. Good luck, and we'll see you next time. Goodbye.